up until this point, we have discussed the three types of bonding. Who can tell me what are those three types that we've talked about? Tony?
Metallic, ionic, covalent.
Metallic, ionic, and covalent. All right, so metallic is pretty simple. It's just metals. What's the key phrase we need to remember for metallic?
Thank you.
Key phrase.
Sea of
mobile electrons, okay? That's why they're good conductors. They conduct electricity well as heat, okay? That's pretty much all we're talking about with metallic. You got to know their properties. Ionic. What's the key word with ionic bonds? Transfer. There's a transfer of electrons. There's a give and a take. That's why we have a plus and a minus. You get those charges that form, okay? Electrostatic attractions, what holds those bonds, they're pretty strong. We'll talk about bond strength here in a little bit. Then we have covalent. What's the key word with covalent? Sharing of electrons. All right, so we're going to take a look at their electronegativities. When you have equal sharing, what's it called in terms of polarity? Equal sharing is what?
Equal sharing. Non-polar.
Non-polar. Good. Non-polar is equal sharing, so unequal sharing would be polar. Okay, and when you have a polar bond, one side is more negative than the other, and the other one is more positive. Now, it's not like ionic exactly. There's slight negative and slight positive charges. All right, that's dealing with difference in electronegativity values. Bless you. All right, so it's kind of a brief overview. Now, when we start talking about hybridization here, just very briefly, and when we start discussing drawing molecules, all right, it's all dealing with covalent compounds, guys. Ionic, the way that we drew those, where we drew the brackets around them with their charges, all right, that's how we draw ionic bonds. All right. Covalent, though, we've drawn single bonds between different elements up until this point. Now we're going to take a step further and draw actual molecules. All right, multiple atoms and how they come together, and we're going to start figuring out their shapes from there. So before we do that, hybridization is the first thing we're going to talk about. It's a mixing of two or more atomic orbitals. Why? To make equal energies. Guys, you're looking to lower the overall energy. This is on page, what? 10. Page 10. Okay? Equal energy. So it's trying to lower that overall energy within a bond. So if we think about it, what's happening is we have we'll do it here in a second. Let's just jump right into carbon. Okay, here's our example. What I want you guys to do is to write out the noble gas configuration for, actually not noble gas only, but the orbital notation. Orbital notation. It's been a little while since we talked about it. Go ahead and do it. There's what our noble gas notation would look like for carbon. Now, when it comes to the boxes, guys, how many boxes does the S block have? How many orbitals does it contain? It's got one. Okay, so what I'm going to do here is to show the idea of what's happening with hybridization. Okay, so we have the 2S block right here. We have two arrows inside of it. Then we've got the 2P. Now, we should know by now from review that the 2P, is higher in energy. Right? That's why it fills in the 2S first. Okay, it goes in the lowest energy, then it fills in the 2P. Well, what hybridization wants to do is it wants to combine orbitals, right, mixes them together to provide an overall lower energy. So we can see that, hey, this one's low, this one's higher, but what they'll do is they'll come together to create a new hybridized orbital that's a mixture of both. Think about it. When you think of hybridization, what's the first thing that pops into your mind? Hybrid what? Hybrid cars, right? That's typically what people think about at first, all right, is, electric vehicles and gas. They combine the two together into one. So when we talk about orbitals here, guys, you've got two combining to one. Well, how many boxes, how many orbitals total do we have here between the 2S and the 2P? There's 4, right? Because there's 4 boxes. So our new hybridized orbital is going to look like this. Okay, it's what we call we'll get there in a second. How many electrons, though, do I have? It's still the same number, right? 4. So I'm going to fill those in like we've done before. So now what this becomes is this becomes the sp3 hybridized orbital. What's the shape of the s orbital? Do we remember?
Like a sphere.
It's a sphere, okay? So I can't really draw it. All right, something kind of like this. There's my sphere. All right, P is a what?
It's like an infinity.
Yeah, it's an infinity, like a dumbbell. So what happens, now the shape with the sp3 hybridized orbital is you get a little bit of both. So you've got kind of like a sphere part, and you've got part of a dumbbell there, okay? And that's what they all look like. So it's the best of both worlds, so to say. Now, I'm just showing you more than what we need to know. Okay, don't worry about the shape too much. Just know, guys, the big idea with hybridization is that the new orbitals that form here, this sp3, okay, is lower in total energy because we're not as high as what this P was, so we have a lower overall. And again, atoms want to do that because it's lower energy. Does that make sense? It's all about how much energy is involved. Tony. Lewis structure. So Lewis, we've heard that name before already, right? In what? Lewis dot diagrams. So we know that this is going to continue along that same line. What did we look at in Lewis dot diagrams? Valence electrons. Guys, same idea here. We're going to use those valence electrons because, first off, valence electrons are what?
Cool.
Cool? Okay. What are valence electrons? They are the outermost, okay? They're the ones, guys, that can move. They're the ones that are involved in bonding. All right? So, first things first, when we do a Lewis structure, element symbol, that's the nuclei and the intershell electrons, very similarly to what we've already done with Lewis dot diagrams. Dashes. We've already seen dashes when we did covalent bonds. Right? They were an electron pair that was being shared. Okay? One dash is how many electrons? So when we drew out structures last week, I think we did BR and
That's 2.
CL, I think, something like this. And we had it in between. How many electrons are in a bond? 2, okay? So every time you see a dash, it's 2 electrons. All right, so single bond contains 2 electrons that are being shared. Now, this is something that's going to be new. Dots are unshared electrons. We've seen them with our Lewis dot diagrams. They want to exist in what? Do they want to exist by themselves as one single dot, or would they rather have 2? 2. They're called lone pairs of electrons a lot of times. And that's going to be a big idea. Lone pair electrons. Now, I will abbreviate that, guys, a lot of times as LPE, lone pair electrons. So maybe you want to jot that abbreviation down just so you kind of know how I'm discussing things and how I write it down. Now, as we go through this process, it is a process. If you skip a step in the process, it will make it very difficult. If you follow the process, the more practice you do with it, the easier this gets, and this is really something not that bad at all. Follow the steps to the process. And the best way to master this, guys, is to practice over and over and over again. So here we go. First step is we're going to determine the number and type of atoms. All right? Pretty simple. You'll see how I'm going to read through all these and kind of highlight the most important pieces, and then we're going to get into some practice, and you'll see how they all come together. Number 2 is going to determine the total number of valence electrons. Total number. So that's all of the atoms combined. All right? So have your periodic tables out if you don't have them out already. We're going to arrange the atoms to form a skeletal structure. The first atom, guys, in the formula is typically the central atom, unless it's otherwise specified. There's one element that you could see as the first one that cannot be central. What is the one element on the periodic table that cannot be the center atom? Tony? Why would it be hydrogen? Because it does say it right here. But why? What's the reasoning behind it?
Because it's the first.
Okay, hydrogen could be the first, but why can't we have hydrogen, guys, in the center? What's unique about hydrogen that we learned last week? Alex? It only needs 2 valence electrons, right? Because it's in that first energy level, guys. It can only have 1 bond with it. Your central atom is going to have 2 or 3 or 4 bonds, maybe even 5 to it, to make it the whole structure. Hydrogen can't. Hydrogen can only have 1 bond, therefore it can't be your central atom. So keep that in the back of your mind. We're going to add up our used electrons, meaning from bonds. Okay? Then we're going to subtract this. We're going to be bookkeeping as we go along. All right, you'll see how this all plays out in a minute. Then we're going to add electron pairs after we add bonds, subtracting 2 from each one to try to get to what's the magic number that every element's trying to get to?
8.
8. Okay, 8 is that octet rule that we've talked about. Step 5a. Okay, there's this 5b that will come later on. Count the number of electrons in the structure. Make sure the number of valence electrons used equals the number of available. All right, and that all atoms are satisfied. If they're not satisfied, we'll move on to the other steps. I've thrown a lot at you already. We're going to take it piece by piece. Let's start some practice right now. So, first step, we're going to start with NH3. That's ammonia. We have not gotten into naming yet. We're doing the structures before we learn how to name. So we will come back again next week after our test. We'll start learning how to name compounds. All right, so I've given you guys the formulas and the names, I think, in a lot of places in your notes. NH3 is ammonia. Have you guys ever heard of ammonia? You probably used it before, probably smelled it. Okay, cleaning product. We'll use it later on in the year, too, when we do one of our labs. But anyway, NH3. First step I need to do is what? First step I need to do, look in your notes. What's step 1? Yeah, determine the number of atoms. So, how I do this and how I bookkeep is pretty simple. How many nitrogens do I have?
1.
I've got 1. So I'm going to put a 1 down. This is going to be my number of atoms. Nope, I'm sorry. Yeah, it is. And then, how many valence electrons does nitrogen have? It's got 5. So in the parentheses, guys, I have to do a little math to figure out the total number of valence electrons. So I'm kind of doing steps 1 and 2 all in one. Okay, steps 1 and 2 all in one. So in my parentheses is going to be my number of valence electrons. You with me so far? Now, I'm going to add that to the other elements that I have in my compound. So first I need to know how many hydrogens I have. How many do I have? 3. So there's my number of atoms. How many valence electrons does hydrogen contain? It's got 1. Those are all my atoms that I have in this formula. So now that's going to let me figure out the total number of valence electrons I'm working with. When you do the math, how many would that be? 8, okay? So we have a total of 8 valence electrons that we're going to use in this formula. Not that we're going to use, we have to use. Okay, we're going to use all of those up because each element is bringing a certain number to the party. Okay? They don't want to be left out. They got to use their electrons. They're all coming, because again, covalent bonding means what's happening with the electrons. They are being shared. So all the elements are bringing electrons to the table to be shared for the entire structure. So that every element that's in the compound is going to have their magic number of what? 8, except for hydrogen will only have 2 because it's happy with 2. So, that's my step 1 and 2 kind of combined. Step 3 is to do what? What's step 3 say? In your notes. Skeletal structure. So, we got to figure out what my central atom is going to be. That's typically the first one unless you see hydrogen, then go to the second one. So, nitrogen's first, that's going to be my central atom. Skeletal structure, guys, it doesn't really matter right now the order that you make those in. When we get to Vesper, that's going to dictate the shape that we draw more than anything else. So for right now, the skeleton one may be our final structure. It may not be our final structure. So we're just going to put something down. So typically I start over here on the right-hand side, and I kind of go around the horn and just draw in all my other elements. Okay? Step 3, if we looked at it, it says skeletal structure, and then we're going to connect our atoms. All right, we're going to connect them using a single bond. We'll start off with a single bond. So I'm going to draw a line. 1, 2, 3, because I had 3 hydrogens. Now, in each bond, in each line, how many electrons am I using? 2. So if I have 3 lines, how many electrons did I use? So I'm going to subtract those out. I've got 6 bonding electrons. Okay. How many electrons will I have left over?
2.
Okay. Now, step 4 says once we have bonds between every element, what are we going to use those extra electrons for? Read in your notes. Step 4. 8, absolutely. So if we look back at step 4, add electron pairs. Now let's think about it. Okay, save your central atom for last. Start by putting lone pairs around what these are called satellite atoms. Okay, what's a satellite do? It kind of orbits around something. So guys, these atoms are sort of quote-unquote orbiting around your central one. Start with the satellite atoms first, then go to your central atom last. Now, in this case, will our satellite atoms have any valence electrons around it? Why not?
Because they have the maximum.
Exactly. Hydrogen, guys, can only hold 2 electrons. Each hydrogen atom has 2 because there's a single bond. So I've got 2 here, 2 here, 2 here. So the hydrogens are all happy. So where do you think my extra 2 electrons are going to go? It's going to go on nitrogen here at the top. So I'm going to subtract those out. Those are my lone pair electrons. I've got 0 left over, which is a good thing. I've got to use up all of my electrons. Okay. Now I'm going to take a look at my structure. I want to make sure that every element is satisfied. We already know that hydrogen is. We just talked about that. Because each hydrogen has 2 electrons, which is its magic number. Nitrogen needs how many? 8. How many does it have? Well, let's start with the bonding ones. How many are right here? 2 right here. 4, 6, and then we've got 1 lone pair, which is 2 electrons. 6 plus 2 is? Are we all good? Absolutely. There's my structure for ammonia. Okay? It's that step process. Figure out the number of valence electrons you have first. Draw a skeletal structure using single bonds to start with. Then add lone pairs with any extras that you may have till they get to 8. Let's do another example here together. SiF4, silicon tetrafluoride. What's my first step? I'm going to give myself some space and erase this. What's my first step, guys? Determine the number of valence electrons. So, I've got 1 silicon. How many valence electrons does silicon have? 4. Plus, how many fluorines do I have? How many valence electrons does fluorine have? 7. Oh, we got a lot of electrons here. When you do the math, 4 times 7 is? 28 plus 4 is? 32. So we've got 32 valence electrons that we've got to use here. This is where bookkeeping becomes crucial, when we've got a lot of electrons. We can't use more than what we have brought to the party. Okay, you can't go and just create more. You can only use what you've got. Those elements bring into the table. So what's my central atom going to be? Silicon. Then I'm going to put my fluorines around it. Again, it doesn't really matter the order. We'll talk about the order a little bit more when we get into Vesper. Connect them with single bonds. If I have 4 bonds, how many electrons is that? 8. So 8 bonding electrons, VEs I'm calling them. 32 minus 8 is? 24. So now we have 24 other electrons that we've got to use. So start by putting lone pairs around your satellite atoms. How many more does this fluorine guy need? He's got 2. He's trying to get to 8. How many more does he need? 6, right? 6 will get him to 8. So let's start doing that. He needs 2, 4, 6. So he's got 8 total. Okay. This guy's going to need 6 as well. Same with this one over here. Same with this one right here. How many electrons did I just add in there? Oh my goodness, look at that. 24 is lone pair electrons. So I've got 0 left over. Go back and double check. Is every element happy? Start with your satellite ones. Is this fluorine guy happy? 2, 4, 6, 8. He's good. 2, 4, 6, 8. That one's good. 2, 4. Can't do it. 4 down there. 6, 8. 2, 4, 6, 8. And then is silicon happy? 2, 4, 6, 8. Every element's good there. Now remember, this is very similar to covalent bonds that we drew last week. We drew lone pairs last week. We drew bonds between them, but it was just between two different elements. Now we're taking it a step further. We have multiple elements to worry about. Okay? I want you guys to try Bri and CH3Br. So we've got bromine, one of those, 7, plus 1 iodine, which also has 7, so that's a total of 14 valence electrons. Now, with this one, when we have two elements, that's it. Is there really going to be a central atom, guys? No, because you only have two, so you just put them next to each other. Bromine, iodine, put a bond between them. Subtract out those two bonding electrons. We've got a total of 12 that are going to be lone pairs. Each of them needs 6. Minus those 12 for lone pair electrons, 0. Bam, that's what we got right there. Questions? Now we'll go on to the next one, a little bit more challenging. So we've got 1 for carbon. It's got 4 valence electrons. Plus we've got 3 hydrogens, which each have 1. Plus 1 bromine, which is 7. When you add all those up, how many valence electrons do we have? 14. 14 valence electrons. What's my central atom going to be? Carbon. You're going to find, folks, that carbon is going to be a central atom a lot of times. Why do you think that might be? How many valence electrons does it have? 4. There's that question, right? Is it easier to gain 4 or lose 4? Carbon in group 14, silicon's another one. They are the best sharers on the periodic table. Okay? When we talk about organic chemistry later on in the end of the year, you're going to see that the backbone are all carbon atoms to those. Anyway, we'll get there later on. Now start putting them around. Doesn't really matter, okay, what order you go in. Just put them around that central atom. There's going to be Br. Connect them. So there's 8 bonding electrons. I've got a total of 6 left. Will hydrogen get any dots around it? Absolutely not. And I see this every year, that people just start going through and putting dots in there. Folks, if you see hydrogen, if you put hydrogen down, you're losing all the points. Okay? Hydrogen cannot have any dots because it's satisfied with 2, which is in the bond. So bromine, we'll get all those lone pairs. Sorry, it's kind of running into everything else. All right, minus 6, 0, good. Questions? Easy? You think it's going to stay this easy? No. All right, and let's take it another step further. So now, what happens if we run out of electrons before everybody gets satisfied with 8? Okay? There we go. Double bonds and triple bonds, guys. Double bond would just be 2 lines. Therefore, 2 lines. Remember, every line you see is 2 electrons. If you see 2 lines, how many electrons is that? 4. If you see 3 lines, it's going to be 6. But again, the key idea is that they are still being shared. They're still covalent bonds. All right? So, we need to use multiple bonds when there's not enough valence electrons to satisfy the octet rule for everybody. Guys, as soon as I introduce double and triple bonds, typically, that's when people start putting them in all over the place. They are a last resort. Okay? Double and triple bonds are a last resort. Only when you absolutely have to use them. Don't start going double bond and triple bond crazy just because you think it looks cool having more than one line drawn between atoms. Okay? It's not going to get you to the right shape. So, if we look back at step 5, remember that was step 5A. If they're all satisfied, that's great. But if they're not, then we go on to step 5B, all right, which I believe is at the top of the next page in your notes. Okay? We'll get there in a second. Let's just talk for a second. Which do you think is the strongest? So we're still in covalent bonds. Between single, double, and triple, which do you think is going to be the strongest bond? Why? Absolutely. It's got 6 electrons, guys, versus only 2. It's going to be the strongest. It's going to be the most energy holding that bond together. Which do you think is going to be the longest, though? You said same? Or did you say single? Why do you say single? Absolutely, guys. Think about strength with things. Okay? The less strength something has, the further you can push it or pull it apart, All right, and it's still together. If you got something that's really strong, think about where your reach could be. Something you're going to be stronger holding on to something when it's closer to your body versus when it's farther away. Same idea here with bonds. The longest one is going to be single, which then is the next one's going to be what? What's the next longest one? Double, and the shortest is going to be what's left over. There you go. I know it's a Monday. So we got the longest over here. And we've got the shortest right here. I may want to add this into your notes, folks. Highly recommend adding this into your notes. So triple is going to be the strongest. What's going to be the next strongest? Double. And then weakest is going to be single. All right? If the octet rule has not been satisfied, then we form multiple bonds. Remember, this is a last resort, so let's do this one together. Other steps are still the same. First thing we got to do is figure out what? Valence electrons. So we've got one carbon, which has 4. We've got 2 hydrogens. How many does hydrogen have for valence electrons?
1.
Plus oxygen has how many?
6.
Okay. So when you add those up, 4 plus 2 plus 6 is? Not 11. You bring that up, Tony. You said 11. Think about it like this, guys. Can you ever have an odd number of valence electrons? No, because you have lone pairs, and you have bonds, which are a pair of electrons. Everything is in pairs. You're not going to have an odd number. So if you do that and you make that mistake and you see an odd number, okay, you did the math wrong. Go back and double check it. So we've got 12. My central atom is going to be what? Carbon. So put the other ones around it. So the process, folks, is exactly the same as it has been. All right? There's my skeleton structure. Connect them with single bonds. Subtract those out. I've got 6 left over. All right? That I'm going to use as pairs. All right? So start with your saddle atoms. Do my hydrogens get any other dots? No, they're satisfied. So I'm going to then put my dots where? On oxygen. So oxygen has 2. It needs 6 more to get to 8. Well, I ran out. Are all my atoms happy here? We said hydrogen was good. Oxygen's good. Is carbon good? No, it's not. So now we've run out of valence electrons. We can't just add any more into our system, into our molecule. We've got to use our electrons from somewhere else. And that's where we're going to take one of these lone pairs. Okay? Now, everything is dealing with sharing, right? In these other bonds, one atom of carbon is contributing to hydrogen. They're sharing. Well, there's a lot of energy still going on. There's strain in this molecule because carbon doesn't have 8. So oxygen is willing to give up and contribute and share an entire lone pair to carbon so that carbon can have 8. So this is what it's going to look like. We're going to draw arrows to show when a double bond is going to form, and we're going to redraw our new molecule. So it's going to look something like this. Now notice what I did here, last thing, and then I'll let you guys have a break. Notice what I did with my lone pairs. Did I leave them on the sides? No, I kind of moved them right to where they were angled. Why do you think that might be? Those are lone pair what? What do the dots represent, guys? Electrons. What do we know about electrons? They are same charge. They want to be close to each other or far away? Well, notice, how many electrons do I have in these two lines? 4. So these guys are going to start to shift and move away a little bit further from this double bond. That's for tomorrow, though. Go ahead and take